Hello everyone, today in this video we are going to talk about self-induction, and after this video you should be able to define self-induction and derive and apply the formula of self-induction. So we know when we change the magnetic flux through a circuit, an induced current or induced EMF will be produced. So similarly in this picture you can see by moving the magnet we are changing the magnetic flux through this coil and we are getting the current or EMF in the circuit. So this is called electromagnetic induction and it was first demonstrated by Faraday. There are two types of electromagnetic induction. One is self-induction, another is mutual induction. So in this video we are going to talk about self-induction. So self-induction is a property of a coil to oppose the change in current flowing through it. So as you can see out here we have a coil or solenoid, or we can say even an inductor. So another name for solenoid is inductor. So right now there is no magnetic field, so when I switch on this the current will flow and magnetic field will be produced. Now you can see there is change in magnetic flux. Previously there was no magnetic field, now there is magnetic field. So due to this change in magnetic flux an induced current will be produced. So according to Lenz's law, induced current will be produced in such a way that it opposes the change in magnetic flux. So as the current is increasing on switching on the circuit, so induced current will try to flow in opposite direction. So when we switch off the current through this coil, the flux through the coil again changes from something to zero. So that time also there will be induced EMF, and that time as the current through the circuit will decrease, that time the current will flow in the direction of actual current. So you can see when I switch off, induced current flows in the same direction of the current. So this property due to which the coil opposes the change in current flowing through it is called self-induction. Now we will see one video in which the change in magnetic flux through a circuit changes the current in the circuit. Out here a bulb is connected through an inductor or solenoid, and when we insert this iron inside the inductor the magnetic flux changes and the current will increase or decrease accordingly. On taking it out the current decreases, and on putting the rod back to the circuit increases the current. So the direction of induced EMF will try to oppose the cause, and the cause is change in current. So when the current increases the induced EMF will be in opposite direction. When we switch off the circuit the current decreases, that time induced current will be in the same direction of current. So when the current through an inductor changes there will be induced EMF which will try to oppose the cause, and this EMF is called back EMF because it opposes the cause. So now we'll define coefficient of self-induction. So when we change the current through this circuit, the flux through the circuit also changes because of the magnetic field produced by the coil. So we can write the magnetic flux depends on the current. So more the current, more the magnetic field, or more the magnetic flux. So if you remove this proportionality sign you will get a constant. So we'll write flux is equal to L into current. So this L is a constant called coefficient of self-induction, and the back EMF produced by this coil is given by EMF is equal to minus d phi dt. So this is Faraday's law. So if you put the value of 5 from here, then you will get EMF is equal to minus L d phi dt. So minus sign is coming because the EMF will try to oppose the cause, and that is Lenz's law. Now let's define the coefficient of self-induction, that is L. This is the formula for induced EMF. So in this formula if you put di upon dt is equal to 1 ampere per second change in current per unit time, that is di upon dt is 1 ampere per second, that time we will get EMF is equal to coefficient of self induction. So now I can define self induction. So self induction is equal to the induced EMF in the coil when the change in the current in the coil is 1 ampere per second. If we change the current through this circuit by 1 ampere in 1 second, then whatever induced EMF will be produced in this circuit will be the coefficient of self induction of this coil. Now we'll find the unit of self induction. So I'll take this L this side, so L will be EMF into dt by di. So now I'll put the unit of EMF, dt and di. So unit of EMF is volt and unit of time is second, and divided by unit of current is ampere. So unit of coefficient of self induction is volt second per ampere, and it is equal to Henry. And there are other units also. So we know L is equal to flux by current. So flux is Weber and current is ampere. Now let's define 1 Henry. I'll use the formula for EMF. So EMF is equal to minus L di dt. So if you put di upon dt is equal to 1 ampere per second, and if this E is 1 volt, then the coefficient of self induction will be 1. So I am writing the modulus because I don't want to write this minus sign, so this modulus will take away the minus sign. So if we change the current through this coil by 1 ampere in 1 second, and if the induced EMF is 1 volt, that time the coefficient of self induction of this coil is 1 Henry. So now we'll find the dimension of coefficient of self induction. So flux is equal to Li. So L is equal to flux by current. So I know flux is equal to magnetic field into area, and I'll replace this magnetic field. The force on a charged conductor is equal to charge into velocity into magnetic field. So instead of B, I can write F by QV. So if you put the value of B out here, then you'll get L is equal to F by QV A by I. So now I'll put the dimension. For force it's M1 L1 T minus 2, area is L square, charge is AT, velocity is L T minus 1, and current is ampere. So if you solve this, you will get this. So this is the dimension of self induction. So now we will find the expression of self induction of a long solenoid. So this is the solenoid we are taking, or we can say it to be inductor also. So it is having n turns and length is L. So let n be the number of turns per unit length, and we are applying slowly changing current I through the coil. If n is the total number of turns, then number of turns per unit length is equal to total number of turns by total length. So I can write small n is equal to capital N by L. So your capital N will be small n into L. So the magnetic field inside this solenoid will be given by B is equal to mu naught Ni. This is the expression which we have already done in our previous classes. So the magnetic flux linked with this coil is given by flux is equal to magnetic field into area, but we have n number of turns, so we'll put n also. So now I'll put the value of B. So B is mu naught Ni, A is the area of the coil, and instead of capital N I'll put small n L from here. Now we know the formula, L is equal to phi by I. So I'll put the value of flux from here, and current is I. Now this I and I get cancelled, so we are left with L is equal to mu naught N square A into L. L is the length of the coil. Now I want to put capital N in the equation. So in order to put this N, I will multiply and divide L this side. So now inside I'll get n square L square. So n square L square is capital N square. So final expression is L is equal to mu naught n square A by L. And we can use this formula also. In some of the cases total number of turns will be given, and some of the questions number of turns per unit length will be given. So you have to choose the formula accordingly. So now if you want to find the EMF, the back EMF or induced EMF produced in the coil, then you can use the formula, that is Faraday's law. So if you put the value of L, you will get the total EMF. Negative sign is coming because induced EMF opposes the cause. And there are some phenomenon associated with self-induction. So when we switch off the circuit, we get the spark. When we switch off the circuit, the magnetic flux through the circuit decreases and there will be induced EMF in the direction of current, and the large amount of current is produced, due to which the air is ionized and we get the sparks. And in order to reduce the self-induction, the wire inside the resistance boxes, they are kept in this way, so that magnetic field produced by one wire is cancelled by the magnetic field of the other wire. So if there is no magnetic field, there is no chance of magnetic flux or change in magnetic flux, so there will be no induced EMF produced in this. So now let's solve some question. So we have to find the self-inductance of a coil. Magnetic flux is given 40 milliweber and current is given. So flux is 40 for milli, I'll write 10 to the power minus 3. Now we have the formula. Current is given, flux is also given, so we can easily find the self-inductance. So unit will be Henry. So now out here 12 volt battery is connected to 6 ohm. That means current is not given, so but we can find the current using Ohm's law, and inductance is given, so we have to find the induced EMF. So from here we'll find the current and time is given, so di upon dt is there. Now we can find induced EMF easily using this formula. So in this question there is a solenoid. Inside the solenoid there is air only, so that is why it is written air core solenoid, and the length is 50 centimeter, so we need to convert it into meter, and radius is also given 2 centimeter, and it has 500 turns, so we have to find L, self inductance. So R is given, so this is the formula. L is equal to mu naught, so this is the value for mu naught. N is given, number of turns. Area we can find out, pi r square from here, and length is given, so we can easily find the self inductance. Again we have another air cored solenoid with length 30 centimeter, area of cross section is 25 centimeter square. So out here area is given, but it is given in centimeter, so we have to convert it into meter square, and number of turns are 500, and current is also given 2.5 ampere, and the current is switched off from 2.5 ampere to 0 in 10 to the power minus 3 seconds. So we have to find the average back EMF. Now you can find area. Next you have to find the self inductance, so you can use the same formula. L is equal to number of turns are given, area is given, length is also given. So next, then after finding L, you can find the back EMF, that is minus L di dt. So change in current is 2.5 minus 0, and time is 10 to the power minus 3. Again one more question. A toroid is given So toroidal solenoid means two ends of the solenoids are joined together, and it has air core, so that means we have to use mu naught, and it has the radius of 15 centimeter, and area of cross section is also given. So this radius is the radius of toroid, not the solenoid, and they are 1200 tons. So we have to find the self inductance of the toroid. So the magnetic field due to a solenoid is given by mu naught Ni. So we don't have small n, we have total number of turns. So the formula of small n is equal to capital N by length, L, length of the solenoid, and length of the solenoid is the circumference of the toroid. So n instead of L we'll write 2 pi r. Now we can find the magnetic field. So this is the formula I was talking about. So we can find the flux now, and we can find the coefficient of self induction easily. So I think this is the end of the video. Please don't forget to like the video and subscribe the channel. Thank you.